Welcome to the course on plasma physics and applications. Today we will discuss collisional transport in plasmas. Even if collisions play a relatively minor role in plasma that are hot, which is the case of course of plasmas for magnetic fusion, they are crucial for determining the plasma resistivity and the transport of particles and heat. The former characterize uniform plasmas, as you have seen in details in the first part of this course, but today we will address the latter, which characterize non-uniform plasmas. In particular, we will look how collisions determine the transport in real space of particles and heat. We will start with a general discussion on the random walk and its relation to classical diffusion, both as a general reminder and because this approach will enable us to treat the complex situation of the magnetically confined fusion plasmas in a very simple way. We will prove that the heuristic random walk model does indeed correspond to the diffusion process in the case of an unmagnetized plasma. And we will see how the plasma sets up an intrinsic electric field to maintain quasi-neutrality called the ambipolar field, and how this leads to a diffusion that is equal for ions and electrons. This is the so-called ambipolar diffusion. We will treat the case of the magnetized plasmas on the basis of the random walk concepts, so a very simple mathematical treatment, and we will distinguish particle and heat transport and parallel and perpendicular directions with respect to the ambient magnetic field. Naturally, for a magnetized plasma, cross-field transport is the crucial element for confinement. Just to start reminding ourselves what a random walk is, you can see here two simulations of a 2D situation in which we simulate on the left the evolution of a single particle which undertakes statistically independent steps. Each step has the same size, but of course in a different randomly chosen direction, as opposed to the right hand side where you see a movie that simulates the evolution of many particles, each of which undergoes a random walk. So you can see the different steps on the left, and on the right the spreading of a cloud, in a sense that represents the spreading of the initially closed particles under the influence on that random walk. So although the average displacement is 0, the mean square displacement, as you will see immediately, is actually non-zero, and that's the crucial element for assessing transport. So having briefly seen the two-dimensional simulations, now we are ready for a very simple one-dimensional calculation of the random walk. Again, we consider statistically independent steps, psi I, each of size psi. So we can see what happens after n steps. After n steps, the displacement will be simply the sum of the steps undertaken. The average displacement will be 0, and average here means taken over many possible random walks. It doesn't mean in time for the same particle. But as we said before, the average of the square of the displacement is not 0. And we'll evaluate in a simple way. It will be equal to the sum of the average of the square of each step plus the cross terms. But the cross terms actually do not contribute because, as we said, all the steps are statistically independent. Therefore, the average of that product is equal to the product of the two averages, which of course is 0. So we only end up with n times, where capital N is the number of steps undertaken, times psi square, where psi is the size of each step. If we define the intercollision time as tau, that means that the number of steps n is equal to the total time divided by tau. We can evaluate the mean square displacement as follows. X square average is equal to n times psi square, which is equal to t over tau psi square which is equal to typical velocity averaged, typical square velocity average times tau times t. And this product, v square average times tau, can be called d, diffusion coefficient. So d is equal to v square average times tau, as we have just defined, or psi square divided by tau. And that is even simpler conceptually and also to apply to the different situations, because that means we have simply the product of the typical step size in our random walk squared times a typical collision frequency, which is of course the inverse of the intercollision time. So here's the idea that we will apply to much more complicated situations, those that actually are needed for fusion. If we identify a characteristic time, or equivalently a collision frequency, and a typical step size in various situations we need to assess, we can evaluate the diffusion coefficient. For example, if we take electrons that are colliding with ions in a fully ionized plasma, we can say the characteristic frequency is that the momentum exchange, nu EI, as you have seen in previous parts of the course. I remind you that in this case the average symbol indicates an average over the Maxwellian distributions in the plasma. And we have a step size that corresponds to the mean free path for such collisions. Mean free path is always 1 over the density of the targets times the cross section for that process. And that's corresponding to the thermal speed for the electrons divided again by the characteristic frequency for the momentum exchange average of the distribution. So we get a simple evaluation of the diffusion coefficient, which is the square of the thermal speed for the electrons in this case divided by the effective collision frequency for the exchange of momentum. So this will help us in a number of situations. The question is, can we verify, at least in a simple case, that this approach works and that D has indeed the meaning of a diffusion coefficient? And I propose to do that in the case of unmagnetized steady-state plasma with uniform temperature. So as simple as we can get, but yet a typical case in which we'll try to interpret D as a real diffusion coefficient. We start by the equation of motion for electrons or ions. So the mass times the acceleration is of course equal to the electrical force, Qj times E, plus the pressure force, which is minus grad P divided by the density, plus the friction term, which is minus the mass times the velocity times an effective collision frequency. So this is my friction term. I impose steady state, so no time derivatives. I consider uniform temperature for any species. So that means that the gradient of P is simply the temperature times the gradient of the density. So with these assumptions, I can evaluate my equation of motion. So no time derivative, so that's 0 on the left, equals to Qj Ej minus the pressure term simplified for uniform temperatures and the friction term. So that means that I can have a steady state velocity field, which is Vj, that I can express in with two terms. The first term proportional to the electric field, and the second term proportional to the gradient of the density. The first term has a coefficient which is related to the mobility. I say related because it's pretty much the mobility, except the mobility is defined with the absolute value of the charge. There is no sign. It's the charge in absolute value divided by the mass times the collision frequency, mj times nu j. The other term has a coefficient in front, which is called the diffusion coefficient. For the moment, it's a relatively arbitrary definition, but we will converge towards an interpretation for both cases. So that's dj, which is the thermal speed for species j squared divided by the collision frequency once more. Of course, the thermal speed squared is the ratio of the temperature divided by the mass. We note, as actually Einstein did, that the ratio of the mobility coefficient divided by the diffusion coefficient is simply equal to the ratio of the charge by the temperature. That's so-called Einstein relation. Now we are interested in the flux, which we call gamma for species J. That's the density times the velocity. So we can use the expression of the velocity we have just found, and we get nj times the sign of the charge times mu j times electric field minus the diffusion coefficient times the gradient of the density. Now consider for a moment a zero electric field. In this case, we have that gamma, the flux, is equal to the diffusion coefficient with a minus sign in front times the gradient of the density. This is a so-called Fick's law. It tells us that particles tend to move down a density gradient, which is a very general property, of course. Now we use continuity equation without sources or sinks. So that's dnj dt plus the divergence of the flux for species J equal to 0. And we use that to be combined with the definition of gamma j, or in fact with the result of gamma j as a function of the gradient of the density, so that we come to a final equation, which will be indeed the diffusion equation. So let's do that. Now I assume here that dj is a constant, so that I can take it out of the differential operator. This is just for the purpose of showing the final result. Of course, in a real situation, this may not be the case. And I get to the expression of dnj dt minus dj, diffusion coefficient, times the second spatial derivative of the density equals 0. And what do I have here? I have a diffusion equation. So we have confirmed that, at least in this simple case, as an illustration, this coefficient d indeed is a diffusion coefficient, because it's the coefficient that appears in the diffusion equation for the density of the plasma species J. Now a further consideration is that plasmas tend to be quasi-neutral. In other words, the density of electrons and ions is, if we assume singly charged ions for simplicity, have to be equal. So that means that the fluxes need to be equal for electrons and ions, or quasi-neutrality will not be maintained. And in general, diffusion coefficients, and as the mobilities, are different for ions and electrons. So what happens? What can the plasma do? The plasma, in fact, will set up an electric field that will tend to slow down the faster of the two species and accelerate the slower of the two species, so that actually the two fluxes will be balanced. This is a general effect, general property in the plasma. We'll derive it here, specifically for the case of unmagnetized plasmas, or B0 equals 0, because it's simpler. So we assume equal densities again for ions and electrons. We call it N. Let's write the fluxes. For the ions, gamma I is a mobility for the ions, N times the electric field. Of course, electric field is common between two species, is a property of the plasma as a whole, minus the diffusion term. That has to be equal to gamma E for electrons, which is minus mu E. Remember that the mobility was defined with no sign, so I have to put a minus sign here, times the electric field minus the Fick's law, if you like, term, that is the diffusion term. So the two have to be equal. It means I can extract the value of the electric field for that to happen, which is simply the difference between the diffusion coefficients divided by the sum of the mobilities times grad N over N. So we have a flux that will be common for both species that I can evaluate by replacing the electric field that we have just found in the expression for one of the two fluxes that I have for ions and electrons. It's equivalent because, of course, they have to be the same. So let's take gamma E, for example. So I have minus mu E N times the electric field minus the E times the gradient of N. And I replace the value of E that we have just found. This is my electric field, the diffusion term. And I simply do a simple calculation here. Everything will be multiplied times the gradient of N. So I put that on the right. And I have the different terms, minus mu naught dI plus mu E dE minus mu I dE minus mu E dE. So there are two terms that drop, and I'm left with something like a minus sign in front, a combination of mobilities and diffusion coefficients, mu I dE plus mu E dI divided by the sum of the mobilities times the gradient of N. Now I notice that this is a flux which is proportional with the minus sign to the gradient of N. So that means that the term that's in front of the gradient of N is also a diffusion coefficient. It's a new diffusion coefficient. We call it ambipolar dA. And this diffusion coefficient is a combination of the different terms from ions and electrons. It's a consequence of the electric field, which we also call ambipolar, that was set up by the plasma in order to maintain equal fluxes for the different species and therefore quasi-neutrality. Generally, we can notice that the mobility of the electrons is much larger than that of the ions. So we can simplify the expression for the ambipolar diffusion coefficient and get a feeling for its dependencies. So it's mu I dI plus mu I dE. And then denominator, I neglect the ion mobility. And that's equal to simply the ion diffusion coefficient plus the ratio of the two mobilities, mu I over mu E, times the electron diffusion coefficient. And if I remember the Einstein relations that relate mobility and diffusion coefficients, I can express this as dI plus the temperature ratio Te over Ti times Di. And if the temperatures are similar, that is simply 2 times the ion diffusion coefficient. That is to say that in general, we can say that Di is the smallest of all diffusion coefficients. The ambipolar diffusion coefficient will be larger than that, but it will still be significantly lower than the electron diffusion coefficient. So that means that, as we anticipated intuitively, the plasma is setting up the electric field so that the diffusion of both pieces will occur at a rate which will be larger than the ions, larger than that the ions would have naturally, should I say, and lower than that of the electrons, or again, that the electrons would have naturally in the absence of any plasma effect. Let's go now to the case that interests us the most, that is the case of magnetized plasma, which is the case of fusion plasmas. What we have verified together is that the simple approach of taking a diffusion coefficient, which is simply the product of a typical step size square times a typical frequency, makes sense. With only the caveat we have just found that there may be an ambipolar electric field to set equal fluxes for the different species. But in general, we can actually attempt evaluating the transport by the diffusion coefficient evaluated in this very simple way. We notice that in the presence of a magnetic field, we of course have different directions. We don't have an isotropic situation anymore. We have the direction along the field, for which the dynamics will be very similar to the case of unmagnetized plasmas, except perhaps that the ambipolar field, and therefore the diffusion, may be generated in a more complicated way, which will depend on the specific 3D configuration. So we will not go into that kind of detail, but we just noticed that there will be ambipolarity, so this setting up of an electric field, but it will be more complicated than the simple, say, 1D case we have illustrated together. A crossed magnetic field is the more interesting direction for confinement. We are setting up a magnetic cage to trap the plasma to make fusion happen, and of course the plasma, via transport phenomena, will tend to go at a given rate across the magnetic field, and that's something we really need to keep under control. To go across the field, collisions are necessary, at least to go over distances that are larger than particle orbits. So let's play the game in which we try to identify the step size and the frequency, and therefore evaluating the diffusion coefficient in a simple way. What is the typical step size? So we have particles that undergo their gyro motion, and this particle will probably encounter another particle at a different with a different trajectory that would come maybe from another direction. And what happens when we have a collision between the two particles? There will be, for the, say, orange particle, sort of a jump in its orbit in this direction. And for the blue particle, it will be jump in the orbit in the other direction. So the displacement that will be taken typically upon such a collision will be of the order of the Larmor orbit size, rho L. We are evaluating orders of magnitude, of course. We don't pretend to be very precise in this evaluation, but it's very important to give a typical step size for this concept of diffusion coefficient. So typical step size is therefore the Larmor orbit for the different particles. So we identify that. And the next question, of course, is what is the characteristic frequency? Now we are considering the transport of particles. So the characteristic frequency here is that for the transfer or momentum. But we notice one thing: we need to consider only unlike particle collisions, because the collisions among like particles will only lead to a swap in the position of the respective guiding centers, therefore no net transport. So those actually don't contribute to any transport at all. So the end result of this very simple reasoning is that we have a diffusion coefficient that can be evaluated, for example, for the electrons, and this perpendicular sign indicates, of course, that we're talking about the direction across the magnetic field. So that's the typical step size, the Larmor radius for electrons squared, times the frequency for the exchange of momentum between different species or between unlike particles. Similarly, for the ions, we get the ion Larmor radius and the frequency for the exchange of momentum between ions and electrons the other way around. Now, if we say that the plasma is at at the thermodynamical equilibrium, for example, with two temperatures for ions and electrons that are similar, then the perpendicular diffusion coefficients are also similar, because actually the effective collision frequency difference compensates the difference between the two Larmor radii. So in that case, in fact, we don't need, or the plasma does not need, to set up an ambipolar field to get equal fluxes. So we have a situation in which there's a so-called ambipolarity in a natural way. I also notice, although we will not demonstrate that explicitly, that a diffusion equation that's similar to that for particles is valid for heat. So here's the diffusion equation for heat. The variable here is the temperature, and we have a coefficient chi, which plays exactly the same role as d for particles. It's called the heat diffusivity. And in this case, as we have done before, I assumed that to be a constant, so I could take it out of the differential operator. Chi has the same characteristics of d, and can also be obtained from identifying typical step size and the characteristic frequency, or typical collision time. We have said together the typical step size is the Larmor radius, just like for d. What is the characteristic frequency? Well, it will be the frequency of Coulomb collisions, like in the previous case, but for heat transport, it will be that for the transfer of energy as opposed to that for the transfer of momentum. And that's difference number one. Difference number two is that for heat transport, actually collisions between all particles and not only unlike particles contribute to heat diffusion. We don't care which particles collide as long as they transfer energy. So there is no effect of leading to a net transport at zero if particles are identical. So that means that the evaluation of the diffusion coefficient, although based on the same principle, is somewhat different in quantitative terms. Let's consider both directions along the magnetic field and across the magnetic field. Along the magnetic field, the chi, we call it parallel for electrons, will be the thermal speed for the electron squared divided by the sum of the relevant collision frequencies, though again for the exchange of energy, which I call nu sub E, as you have done in the first part of the course. Electrons and ions, or electrons on electrons. And that corresponds to a constant of the order 1 times the square of the thermal speed divided by the collision frequency for momentum exchange, which we normally refer to. For the ions, will be something very similar, except of course that there will be the collision frequency between ions here and the ion thermal speed squared. And we can notice, simply looking at these two expressions, that the parallel heat transport will be dominated by electrons. In other words, electrons will contribute to the transport along the magnetic field of heat in a much larger proportion, because of the much larger value of the thermal speed for similar temperatures than that of the ions. Let's look at the direction across the magnetic field. We do the exact same reasoning, considering the appropriate collision frequencies, and we get something for the electrons that's of the order, although there's a factor here, of rho LE squared times the collision frequency for the momentum exchange. So it's not very different from the diffusion of particles. And for the ions, again, it's something that refers to the collision frequency between ions and ions. But because the Larmor radius of the ions is so much larger than that of the electrons, the perpendicular heat transport will be dominated by the ions. So the opposite situation to that of the parallel heat transport. In summary, in this lecture we have gone back to some of the basics of plasma physics to study the classical transport mechanism in the fusion plasma. We have seen the classical diffusion results from the random walk of ions or electrons that undergo Coulomb collisions, that is, collisions dictated by the electric field. In the presence of a background magnetic field, the transport across this field is dictated by the size of the Larmor orbits of the particles. We have seen that the transport along the field is dominated by the electrons, while the transport across the field is dominated by the ions. In the next lecture, we'll compare the predictions of this classical theory with the experimental data from fusion devices, and we'll discuss how we can actually go beyond the classical paradigm and explain the experimental data and what are the transport mechanisms that actually play in the fusion devices.